At point P, the stress tensor is given in megapascal with respect to Px1, x2, x3 by this stress tensor matrix. You see that the stress tensor matrix is symmetric. So determine the eigenvalues, the principal values, the maximum shear stress, the transition matrix for the rotated principal axis, Px1 asterisk, x2 asterisk, and x3 asterisk, related to the Px1, x2, x3 axis. Now, observation, as we did before, look, you set sigma 1 greater than sigma 2 greater than sigma 3. So, as pointed out before, you see, this example we already did. For n3 is equal 0, n1 is equal n2 is equal plus or minus 1 of square root of 2, for which tau max is sigma 1 minus sigma 2 divided by 2. For n1 is equal 0, n2 is equal n3 is plus or minus with square root of 2, 1 of square root of 2, for which tau s max is sigma 2 minus sigma 3 divided by 2. And n2 is equal 0, n1 is equal n3 is equal plus or minus 1 of square root of 2, for which tau x max is sigma 3 minus sigma 1 divided by 2. You see? Let's calculate the eigenvalues of this matrix, sigma ij. Now, sigma ij minus lambda I, you see the determinant of this matrix will be 0. So, sigma j minus lambda I will be 2 minus lambda, 2 minus lambda, 2 minus lambda in the diagonal, the main diagonal. Now, the determinant of this matrix is 0, so we can develop this determinant using the first row. You see, just cross here, it will be 2 minus lambda that multiplies 2 minus lambda squared minus 1 is here. Then the element over here, you just cross and do the same. This will be equal 0. Now, if you expand or develop these terms, you will come up to this lambda cubed minus 6 lambda squared plus 9 lambda minus 4 is equal 0. Now, by inspection, lambda 1 is equal 1. You can see here, look, 1 cubed is 1 minus 6. This is minus 5. 9 times 1 is 9, minus 4 is 5. So this is minus 5, this is plus 5. So it's 0. Now, if you divide lambda cubed minus 6 lambda squared by 9 lambda plus 4, this is, I'm sorry, this is minus 4 over here. See? Minus 4. You come up with this second order degree, the polynomial here. Now the roots of this polynomial is lambda 1 is equal 1 and lambda 3 is equal 4. So let's order. Sigma 1, the highest, the largest, is 4. Sigma 2 is 1 and sigma 3 is 1. You see, these are repeated eigenvalues. Now you see the trace of this matrix here is 2 plus 2 plus 2 is 6. Now the trace of the diagonal matrix is 4 plus 1 plus 1 is 6. So this is a valid result. Now let's calculate the eigenvectors for each of these eigenvalues. So since the determinant is 0, this is a homogeneous equation with many solutions. So let's plug here a is equal 1. So if a is equal 1, this is minus 2a b plus c. So this you have b plus c is equal to, you see, this a is equal to 1, this is minus 2, this b plus c is equal to. So substitute here, we have 1 minus 2b plus c. C is 2 minus b. this is 0. So this is 1 minus 2b, this is plus 2 minus b, this is equal 0. So this is minus 3b, this is plus 3 is equal 0. So 3b is equal 3, then b is equal 1. So if b is equal 1, you see, c is equal 1. So the solution of this, let's call it P1. P1 is equal 1, 1, 1. For the eigenvalue is equal 4. Now from here you can get the unit vector v1. See, you see this the magnitude of p1 will be 1 plus 1 plus 1 is square root of 3. So this will be 1 square root of 3. Now 1 square root of 3 and 1 square root of 3. So this is v1. Okay, let's write down right here. So v1 is equal 1, let's put here like this way, look, like this. v1 is equal 1 of square root of 3. Now 1, 1, and 1. See, it's easier. This is v1. Okay? Now let's calculate the eigenvector for sigma 2 is equal 1. For sigma 2 is equal 1, you see, 2 minus 1, 2 minus 1, and 2 minus 1. So be 1, 1, 1. Then here you have only one equation and 3 unknowns. So this A plus B plus C is equal 0. Now we can put, for instance, A is equal 1. Let's see, B is equal minus 2 and C is equal 1. You see, 1 plus 1 is 2, minus 2 is 0. So this is the eigenvector. P2 will be 1 minus 2 and 1. You see, there are many solutions. For instance, I could write A is equal 0 and B is equal 1 and C is equal minus 1. So now from here you can get the unit vector, unit eigenvector. See, this is 1 square plus 2 square is 5 plus 1 is 6. So this will be, let's write here, 1 square root of 6. This will be 1 minus 2 and 1. So this is a vector, eigenvector v2. So this 1 square root of 6. This will be 1 minus 2 and 1. Now the third eigenvector we have to find using the cross product. Okay, v1 cross v2. Sigma 2 is equal sigma 3 is equal 1. So it is a repeated eigenvalue. So P3 is P1 cross P2. E1, E2, and E3. Here are the components of P1, and the third row is the component, the elements of row 3. See, the third row are the components of P2. This is P2 and P1 and P2. Let's work. Now E1, you see, look, 1 times 1 plus 1 minus minus 2, so it'll be 3. This is 3 E1. Now the second, the E2 will be, you see, across here. Now you see, you look, this is 1 times 1, you see, minus 1 times 1, or minus here and plus here. So it'll be 0 E2 plus, now E3 you cross here, so it'll be minus 2 minus 1, so it'll be minus 3. Minus 3 E3. You see, it's 3 square plus 3 square is 18. 18 is 9 times 2. So square root will be 3 square root of 2. 3 square root of 2 here. So you can cancel, and cancel. This will be 1 of square root of 2 E1 minus 1 of square root of 2 E3. So this is V3. See? This is equal. Let's put this. See? 1 of square root of 2 of 1, 0, 1. You see? Now it's easy to write. Now we're ready to get the transition matrix. So, you see, A, this is A, you see, just call. AP is equal P lambda, capital lambda. This is A and lambda. A is similar to lambda, you see? Now, AP, what is P? You see, this is V1, this column is V2, and this column is V3. Now, AP is equal P lambda. This is capital lambda here. So this is a matrix P. All I want is P minus 1. You can see? If you read carefully, you see that we want not P, we want P minus 1. So P minus 1 is a transpose of this matrix over here. So let's write down right here. Let's write here. You see what is P minus 1? Look. I will erase this side here, okay? Now, because this is P minus 1, that's the answer. That's a transition matrix. This is P minus 1 is equal P transpose. You see, look, the first row will be the first column. So this 1 square root of 6 and 1 square root of 2. Now, the second row, the second column, 1 square root of 3 minus 2 the square root of 6 and 0. See? And the third row, the third column, 1 square root of 3, 1 square root of 6, and 1 square root of 2. So this is P minus 1. You see? Now, what I would like for you to pay attention is this. So we have a system, let's write here, just for you to understand what is P or is P minus 1. You see, for instance, if I have a vector X, let's write down in the X1, X2, X3 coordinates. Now the same vector Y, you see, will be P minus 1 X. Y, the components of Y will be in X1, X2, and X3. That's the eigenvector. So, you see, P minus 1, okay, apply to a vector on this, let's call this unprimed system, okay? Now, a same vector, okay, P minus 1 times this vector here, apply this vector, give the same vector X, but written using the coordinate in this system over here. Okay, for instance, if I have a vector Y, so I have a vector Y in this system here, to get the same vector in the system X1, X2, X3, this will be Px. You see?